In this chapter, we're going to be talking about exponential smoothing time series methods or models. These have been around since the 1950s, but in the last 2 decades there has been a lot of innovation regarding some statistical models that allow us to get entire forecasting distributions from these methods. So we'll talk later about those statistical models, but the advantage of um, learning these models is that if you want to provide quick, reliable forecasts for a wide range of time series, these models can do so. Now, these are widely used in the industry. You didn't want to use your mind and you wanted to have some sort of an automated method of providing forecasts all the time, you could actually rely on these models. The chapter is going to be outlined as follows. We're going to talk about why these methods are called exponential smoothing methods or models. We will discuss some of the simple exponential smoothing methods that are out there that are really derived from things that you already know, like random walk methods or naive methods. Then we're going to talk about models with trends and seasonality. And finally, we'll close this chapter by talking about some of the innovations that have happened using state space methods, models, and finally, what we really want to do is forecasting. So why are these called exponential smoothing models? Now, the idea here is that any forecast that is produced using the exponential smoothing method is going to be some sort of a weighted average of past observations, with the weights decaying exponentially as the observations get older. So let's take an example here. So let's say we have a time series Y, and we have all the information until from period 1 till period t, and what we want to do is forecast one period ahead. So our forecast horizon is just 1, right? So this is yt plus h, where h is equal to 1. Let's say we just wanted to do this. We wanted to find out what is yt plus 1. Now, what exponential smoothing methods would do is that they would assign a higher weight to an observation that is more recent, like yt, because that's in our information set, and a lower weight to an observation that was, let's say, 3 periods ago, right? So as the observations would get older and older, the weights that you give, or these models give, to those observations are going to get smaller and smaller, exponentially smaller. Okay, so again, these are really reliable methods and have vast applications. Now, these have been around since the 1950s and 60s to produce point forecasts, right? So we're not talking about distributions at all, or the uncertainty associated with the point forecast that we produce, but there have been methods that have been around just to produce point forecasts. But we can also now do, with the innovation in exponential smoothing methods, we can also now talk about distributions, and of course, if we have the distribution, we also know the confidence with which, or the uncertainty associated with those forecasts. So what these models are good at doing is that these can combine 3 different components here. The underlying level of a time series, there's some sort of an underlying level to each time series, the trend or the slope of a time series, and the seasonal component associated with a time series, right? So you have the power of these models comes from the fact that all of these 3 underlying components are going to be uncovered and exploited in producing a forecast. Now, the rate of change of the different components, that is the level, the trend, or the slope of the time series, or the seasonal component, is controlled by what we call smoothing parameters. The smoothing parameters, as we go along in this chapter, are going to be alpha, that controls the level of the time series. And I'll explain what that means, what are alpha, beta, and gamma in a second, how these would change the forecasts. Beta would control the slope of the time series, and gamma would control the seasonal component of the time series. Now, how smooth is the rate of change is going to be controlled by these smoothing parameters. So the selection of the methods is generally based on recognizing some of the underlying features of the trend and seasonal components and the ways in which these would enter the smoothing methods that we are interested in. So these can be additive, damped, or multiplicative, and we'll see what all of this means in just a little bit. Now, the way these models operate or methods operate is that we typically tend to choose the optimal or the best values for the smoothing parameters and the initial states that govern the time series, and then use that for forecasting. Okay, so only in the last 2 decades, like I said earlier, exponential smoothing state space models have been developed that produce identical point forecasts to the methods that were developed primarily in the 1950s and 60s by Brown, Holt, and Winters. But the advantage of these state space models is that they produce entire distributions. So you have prediction intervals that provide the uncertainty associated with point forecasts, which wasn't the case earlier. Now, talking about the smoothing parameters, we have alpha that controls the flexibility of the level, the underlying level of the time series. So if you think about 2 extreme situations here, if we don't have any smoothing, which means that alpha equals 0, the level of the time series never updates, right? So what that means is the series stays at its mean. If alpha is equal to 1, then the level of the series completely updates, and this is identical to a naive method where the level of the time series tomorrow is going to be tomorrow, or the one period ahead is going to be what it was in the previous period. Beta controls the flexibility of the trend. If beta is equal to 0, you have a linear trend. Okay, so you have some sort of a trend in your regression model. And if beta is equal to 1, the trend updates every observation. Okay, so there's a lot of updating going on if there is if beta is equal to 1. And we'll see how that works for different time series if this doesn't make sense at this point. And again, if gamma is controlling the flexibility of the seasonality, right, how much updating is going on in each period. If gamma is equal to 0, the seasonality is pretty much fixed, right? So you have seasonal means and there's really not a lot of updating. But if gamma is equal to 1, then the seasonality updates completely. And this is very, very similar to the idea of a seasonal naive method. Okay, so what we want is a model for the underlying level, trends, and seasonality. We want a model that could capture the level, which is going to be denoted by LT, the trend, which is going to be denoted by BT, and seasonality, which is going to be denoted by ST. So the idea here is, if we ask ourselves, well, how do we even combine these elements? If we can break down a time series into these different components, the underlying trend, the underlying level, and seasonality, how do we combine these elements? So one way to think about this is that maybe we can add all of these elements up. So there's some underlying level to the time series, some trend, and some seasonality. And of course, there is something that we can't explain. So if we're thinking about YT as the time series, that would be equal to what we know, what the level is of the time series one period ago, plus the underlying trend one period ago, and the seasonal component. And this is going to be, if we are looking at, let's say, January of next year, then we are looking at what was it like January of the previous year, right? So that's that seasonal component. If M is are the number of periods, so the seasonal periods. So this is when we think about an additive model. We could also think about a multiplicative model where these components are in fact multiplied to each other. So notice here we have the first component is just the product of the level, the trend, and the seasonality. And the last component is some sort of a remainder that we can't explain, okay? But that also comes from the what we can explain from each of these components. Or it could be a mix of both. So you could have a time series that displays some sort of an additive uh, level and trend, and then this is sort of multiplied by the seasonal component, and again adding here. This is adding here something that we can't explain. So this is again ad hoc, but you can think about some sort of a mixture of both of these methods. Now, the general notation of these models is that these are also called ETS models. Exponential smoothing models are also called ETS models. E stands for what type of a method do we adopt for explaining the error component, something that we can explain. What is going on with the trend component and the seasonal component. So ETS, right? So error, trend, season. And for the error, typically in models, we would have an additive component or a multiplicative component. So we're going to denote additive by A and multiplicative by M. The trend for a time series could be none, right? So you could have a time series that displays no trend. So none, right? N would denote that. It could be additive, which is A, and we'll see examples, so wait for that. Additive, which is going to be denoted by A, multiplicative if it's denoted by M, or damped. So damped could be something that I'll explain later, but if there is some kind of a damping method that we employ, then it is going to be either additively damped or multiplicatively damped, right? So AD would be additive damped, MD would be multiplicatively damped. Now, similarly, you could have something for seasonality, where you could have a time series that displays no seasonality, which is going to be denoted by N, and or seasonality where there is an additive component or a multiplicative component.